someone's folder. Yeah.
So would you guys rather have shorter homework assignments, so like 4 problems from each chapter, or would you rather have, like we've been doing, like 8 problems from 2 chapters? It doesn't matter to me.
I like the idea that 4 from each chapter.
4 from each chapter?
Yeah, I do
okay.
too.
So I'll just assign 4 from networking. They're gonna be super easy, so.
We're still gonna have a week to do it, or should we?
Yeah, no, I'll give you a week to do it. But that means that we'll have to pick up the cadence, right? Because we're gonna cover routing, it should only take 3 days, so that means that your next homework assignment will be coming up shortly. So I'll release the 4 assignments here for networking. Honestly, networking is really easy. Like there's not, like I got a lot of comments from the last class that hey, this is way easier than doing the physical layer, and yeah, it is. But because there's really not a whole lot to the networking layer. Routing it get a little bit harder, but it's not, still for those with networking experience, it's not going to be overwhelming. From at least my experience going through the class 6 years ago, whatever it was now, it was always the physical that was harder, just because I didn't have a electrical engineering background, right? So, yeah, go ahead.
So if we want to do the 8 instead, then to do the 8 will be like 2 weeks.
No, because we'll have to have it on the same grading system. So this is kind of like the evils of democracy question, right? The minority is going to get hosed in this one. So so who would rather have the 4 questions per chapter rather than 8 questions per 2? So 4, and who would rather have the 8 questions all at once? So it's 4 to 3 and a whole lot of I don't cares.
Oh wait, we have a new
voter. You got in, we just had a critical vote.
Oh, what's the vote?
But we went through the notes and we didn't actually have.
Just raise your hand for the first question.
I don't want
Yeah,
homework this
don't
weekend.
worry about it.
Every week homework, or every 2 weeks? Do 8 or 4.
So it won't change the point values. It'd be 8 questions for 80 points, or like it's not going to like impact your grade one way or the other. Cause
You just basically saying once a week or
Do
twice?
every week.
Every other week.
Yeah, so it is a little more work for my grader to do the 8. So it's not like he's going to be butthurt about it, right? Because it's pretty cake to go through and do 4.
Well, I like the 4 because it kind of keeps your homework current with what you're working on, so
Okay.
it kind of reinforces it. But I'm still fine with the vote.
I'm curious, has anyone asked, like, we talked about the midterm yet in detail, what questions are going to be?
So we will have a midterm review, and it's going to follow right when we're done with routing.
The reason I ask is because that might influence how I'd answer.
Oh, okay. So the midterm is going to include everything up until routing, which we are covering today, Wednesday, and probably Monday.
By until you mean through?
Huh?
But you
Yes,
said until
up
the
to
routing.
and including routing.
Is routing still in chapter 5?
It is, yeah,
Okay, so midterm is 1 through 5.
1 through 5.
Okay.
And the midterm only covers stuff that is that we've talked about in class, that we've done homework questions on, or we've done review questions on. So if you're like, and that doesn't include the questions like, hey, I picked the CMDA network for cell phones, right? Because I give questions so that you can have extra reading for
You mean the
your
one that
interest.
in homework 1?
Huh?
You meant the before,
Yeah.
out of the 4
Yeah.
questions?
Yeah, so it won't include that type of material, right? It will only include stuff that I gave to all students. So, but it's still, there's still a lot of material that needs to be covered in there. and we will have a review. And I really caution doing this, but I am open to having an open book exam. I say that because I offer that with reservations, because it often is worse on you to have an open book exam than a closed book.
Why do you say that?
Because you can get lost looking in the book for the right answer and run out of time.
Well, the book doesn't help the
Yeah, the
question.
book's terrible.
Yeah, the book's
Helping computers.
The book, it doesn't help.
Exam would be
I would
nice.
take an open book.
Open that,
If it was open internet, I'd take you up.
Yeah.
This book is terrible, let's not.
Just open up IRC and get everybody in there.
Controlled
I
file.
liked the book until I
So which ones
did
are
the
good on
homework
that one?
questions, and then
The
I'm like,
homework questions are,
Yeah.
They're very off the book.
you
most
you
times.
realize how unorganized the text is.
yeah, when you get
It's a
into
flow. It's just a free flowing.
It's a free flowing, like
Yeah.
a word vomit. And,
Well, you could provide us
Word vomit.
with all the information we need in the questions. For
Yeah.
example, right now, when I do the homework, I have to spend 10-20 minutes searching the book to find one little piece of
Yeah.
information that wasn't provided.
Another
So
one.
I will provide like the detailed information. Like if I say geo, right, I will give you it's 35,800 kilometers, right? I will, if I say, one of the questions is, what do I mean by kilomega, blah, blah, blah. I will write that on the board and you will know. So those kind of details, don't worry about. You do need to know, like, hey, this is how I find bandwidth via a given wavelength. Or, and I will clarify for that. Oh, go ahead, you're fine.
I submitted already.
Uh-huh.
Change one answer. Is it
Oh,
okay?
yeah, do that.
Alright.
Here, right on there, like, new one or something.
Version 2.
All right.
Yeah.
Use this one.
So I will,
Right.
all that information will be there. But I do hesitate to give open book because you really can die in a book.
Yeah, especially this
So,
book.
If it was a different
It's
book,
open.
And I would give an open internet test, but I will make it harder. So I don't know if the trade-offs are gonna be worth that either.
So can you just leave the book up to people to use or not, and then they can decide?
Yeah, I mean, if it's open book, you can decide, but I would caution you, I'm not gonna change the test for an open book. I would caution you though, it's rough.
So for me, like, I use
It's not gonna
the
be
book
graded.
and notes to do homework, so for me, it would be useful reference during the test, as just a refresher.
Yes.
When I'm, like, trying to remember some specific,
So then book of the notes.
But you did say you're also giving us a sheet, right?
You can have one sheet for notes, as much notes as you can fit on that sheet.
Does it
You
have to
can
be
write
like-
really, really tiny. you
One-sided
can
or two-sided?
write it-
Two-sided.
Two-sided.
Two-sided, okay.
I'm not gonna go through and check sites.
Right.
So one sheet of paper, and you can bring pen or paper so
Right
that
on
the
the
line, you
edge.
can make it really small.
Oh, okay.
Right, so you don't even have to use line paper,
Printed.
but one sheet.
Size 4 font.
Does it have to be hand?
Yeah, pretty,
Yeah,
the
so
problem is
that's
that it's hard to do formulas, I mean, it's a giant pain to do formulas, on the computer. Right, so some of the things just might be easier to
So I
write.
write everything on my
Well,
iPad,
tech.
can I use it?
I already have
See,
done that in the
that's- Yeah, I don't know about
I
that.
only use front and back, I swear.
What format are the questions gonna be on? What are the questions gonna look like, I mean, on the midterm? Open answer, or?
Some of it will be open answer, some of it will be just hard number, like probability of this, right? So we did a lot of stuff on the physical, so there will definitely be some kind of bandwidth question. For the networking stuff that we just did, that will probably be your like give me, cause all of that stuff is really kinda easy. But we'll go through so some of you had me for other classes, but the way my midterm reviews look like is I will have the test in my hand. And I will say, so, for blah, 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 right? And I might change some numbers or whatever, and that's how we will go through the
There we
test.
go.
So Wednesdays
Okay.
are the midterm, right?
Huh?
Yeah, it's Mondays or Tuesdays
Midterm
before.
review.
Is this the Monday before or the?
No, I think we voted that they wanted a Wednesday review and a Monday test. That way you could go
Yes.
over the
Yes.
weekend.
Yes.
Great vote.
And right now, that's the way the schedule's looking.
So 2 weeks from now.
The video,
It'll be 2 weeks from
Wednesday
today.
Posted immediately.
Yes.
On 16 already.
That's actually really hard. You don't understand how much I fight that thing to get video posted.
Not apt to agree that.
So if you guys have never used a GoPro, right, it only records in 15-minute segments, and then you have to put them all together. Then you have to create a new video, and then once that video gets encoded again, right, which takes like 4 hours on my Xeon. It takes 4 hours to encode on my Xeon, and then I post it to YouTube, which takes at least an hour, right? So it's.
So Wednesday night is what you're saying.
So.
Thank
You
you.
got
sir.
vacation days, right?
You know, this might just be a beer talking day. Yeah, I have no time for anything. I get a full-time job. My wife is running for school board, which is the worst decision we've ever made.
I saw the signs in
That's
mine,
on the
and I
video.
was gonna ask you if that was her,
That
because
is her.
the name is pretty uncommon.
Yeah. Weirdly enough, there's a lot of churches in Colorado Springs. I don't know why. I mean, my parents are here, my brother's here, but that only is 3 families. There's like 15 families of churches, and none of them are related, or at least not close.
Anything we can do to make her fail?
Huh?
If you ever regret it? Anything we can do to make her fail?
To make her fail.
So this is on the video.
Yeah,
She doesn't
this is getting
say.
posted on, yeah. Wow. Get me killed.
Turn it around.
He said that.
Careful
Yeah.
how you answer this.
So, the best thing that could happen is she wins. The worst thing that could happen is she wins. So, we're in it now.
That's at least on our date night video.
Oh, wow. I spent the first week just trying to figure out how not to go to jail with campaign finance laws. It's crazy. All right, so routing. Everything that we've talked about so far within the network layer has been forwarding, right? How does one router or one network device talk to its neighbors, right? That's really forwarding. That's not routing. That actually, we said, hey, if a device arrives at this router, then it can forward it to a different router via these methods, right? And sometimes there's some internet working issues that we have to go through at the link layer, and we have to deal with that, right? But it's really moving from one packet to the other, or one device to another. We also talked that in a general framework, that the IP address space is hierarchical, so that if it's hierarchical, then it's easy to find a destination even if you don't know exactly where it is, because you can simply identify its network, or the and then we gave you methods to do that forwarding to the network. None of that actually explained the mechanisms for building all those tables. Right? We just presumed that those tables existed. So if the table exists, then we can do all of those things. Now the question is, how do we build those tables? So we're still in the networking layer, right? But now we're actually in the implementation of the actual functionality of the network layer, of moving one packet to another. So far we've been dealing with really simple, my 4-box diagram, which you guys are beginning to hate by now, right? The question is, what do we do if it's not so simple? This is a very simple linear network, and there's only real one path to get the other. And we also talked about spanning, right? At the doing spanning tree at the link layer, where we broadcast out and discover networks that way. So one of the things that that we talked on early on is we could do spanning tree for the network, right? That doesn't function very well in the internet. Why?
Every time a new device gets on, it's gotta start over again.
It's got to start over again, right? We have to go through and flood the network again, discover where things are, right? Is there a way that we could build spanning tree that might be improved upon so that it doesn't have to do the whole network? Well, we could have subnets. Yeah, obviously the whole hierarchical network helps, right? But we still need to find to get to one network to the other. So inside the subnet, inside the Ethernet, where we're all connected, right? We can simply just use spanning tree, and we do use spanning tree. But if we want to move from one network to some unknown network, is there some method that we used in spanning tree that could actually to help us get there? So sort of. So instead of broadcasting, maybe we could just talk to our neighbors. The biggest problem with the whole spanning tree idea is that we needed to flood the entire network to be able to discover where everybody was. We needed to do that in spanning tree because it was not hierarchical. So every device comes with a hard-coded MAC address. You stick it on the network, and in order for that network to function, every device needs to know where it is. There is no parent device that can say, hey, instead of talking to that guy, just talk to me. Right? But in IP, we now have internet hierarchy, right? However you want to visualize it. Right? There are ways to get to, and it's not a perfect tree, right? Some things connect other ways, right? But at least in physical topology, some things connect other ways. But we do have a way to reach networks through the hierarchy. So what if we took an idea like spanning tree, and instead of propagating the whole network where we have no hierarchy, we could just talk to our neighbors to find out where they are. So, and in context of routing, what you were really talking about was in forwarding, we talked about how a device moves one packet from one port to another. In routing, we're talking how does a network move packets from one network to another. So consider the spanning tree that has 6 network devices. Circles, because they're easier. And let's say the spanning tree, even though they're fully interconnected, well, let's not go totally interconnected because it's going to get really messy. Let's just do it like this. Even though they're partially interconnected, there's more than one route. A spanning tree just picks the route, right? So we kill this connection, even though it exists, right? And we might kill this connection, even though it exists. And then we only have one way to reach each device. Problem solved. Routing introduces something else. One, we need some method to fail over. So it would be nice if this, for some reason, dies, then this comes to life. It would also be nice to say if for some reason this is just slow, still alive, right? This comes to life and is used. And in the best case scenario, it would be nice is that we just shared the bandwidth across multiple devices. So we're going to talk about the first two of those scenarios. Because routing can get actually pretty complicated in modern bandwidth load sharing. So, but we'll talk about the methods of doing the first two. That will give you a premise to start thinking about the third, and then we don't have to test it, which everybody will like. So, routing is a method of bandwidth allocation. It's a way that we achieve what we've been talking about so far, the whole course, is how to utilize our network most efficiently, how to fill our pipes. Because as we discussed earlier, filling those pipes allows us to achieve things that we want on the user end, which is we get reliability of service, we get quality of service, so on and so forth, and we get to share movies from Netflix. So routing the other parts that we've talked about for network topology, you can talk about provisioning, right, which is how you build your network, right? And the time span for provisioning networks is months or years, right? Because it requires capital investment. You have to decide what kind of fiber you're going to lay, or are you going to lay copper because it's close? Are you going to buy this switch or that switch, right? These types of provisioning are, on a grand scale thing, can achieve what we talked about on filling our pipes and getting Netflix really fast. But they're long-term projects.
How long did you say it takes to build a network?
Well, we could build one in this class, provided we had brought everything with us in the class period, right? But in a building, takes much longer, and it would take the order of weeks of architecting it and order of months of running all the cables and getting it installed, and then probably just days to get it up and running after that. But it's a long term. And then if you go out beyond this building, right, to the entire campus, it gets much more complicated. Because now you have all sorts of, where are you going to put these big infrastructure places that take actual space? It's not like you're just sticking a switch in the ceiling or something. There's also a thing called traffic engineering, which works on a smaller type of scale like ours. The idea behind that is on the West Coast in the evening, they are using their networks different than on the East Coast in the evening. And that's because on the East Coast, it's a 4-hour difference. So their evening is spent with Netflix, where at the very same real physical time, not time zone, on the West Coast, they're still at work. Right? So there are traffic engineering things that they can do inside the network, and they do inside the network to manage that. And then routing is on the basis of minutes. It is focused down on how do we do a distributed system with individual devices where we can bring new devices online, or they can fail, or they can partially fail with ports, and we can recover. And we need to be able to do that in minutes. And then there's actually a different type of routing, which is called load sensitive routing, which is that bandwidth sharing thing that we talked about that we're not going to cover. Right? How do you do, within seconds, manage hotspots? So if you have traffic congestion for some reason, some big event happens in, let's say, New York, right? And there's a lot of traffic being generated going into and out of New York. Then, and there's also a lot of traffic going into and out of DC at the same time. It may not make sense to go direct from New York to DC. it may make sense to go around it. Right? Those things happen in seconds, and that's also on the network. But it's taking these basic concepts that we would learn in routing and moving it to a quicker time scale with much more complicated algorithms. Also, we're going to talk about routing in the sense of unicast, where one computer is talking to another. What other types of scenarios can we have? Multicast. What's an example of multicast? Huh?
Casting it out to everybody.
Yeah, what kind of application would that be?
NTP?
Twitter. Well, NTP, yes, NTP can be. Huh? Twitter, kinda, right? I think the best one that people are using right now is like Facebook Live, right? Where somebody's doing a live recording and it's going out to multiple computers. It's not the same as Netflix. Netflix is still unicast, right? So when you go to Netflix, you don't have to wait for it to start, right? Otherwise, Netflix probably wouldn't do as well as it does, right? Instant gratification.
But Netflix is hosted for multiple customers, so it should be multicast.
Well, Netflix is hosted for multiple customers, absolutely. Do they deliver the movie at the same time?
Okay, what if we have two customers like requested for
Then it would.
trash for?
No, they
off
can
the packets?
they can send out packets to two. Unicast doesn't mean that I can't send packets to both of you at the same time, right? Unicast means that I have a piece of content that I'm going to deliver you.
Yep.
My computer is fast enough that I can deliver it to you also. And in reality, Netflix actually hosts across the United States, and they use some of the other techniques that we talked about, right, where you just store your content closer. So you pick an AWS farm in Denver, right, and host your content there. But it's still unicast. Otherwise, there'll have to be a start time and end time. It has to be. Then you're just cable TV over the internet. But there are scenarios in the internet right now. I think Facebook Live is probably the best example I can come up with. And it very well may be Facebook Live is done unicast because it would certainly be easier.
Xbox Live.
Huh?
Xbox Live.
Yeah, well, it's just, there's a video coming out from somewhere and it's going out to Facebook, right?
Citrix that hosts the online conferences, Citrix.
Yeah, that might actually be a good example. That's probably a really good example. So you do an online conference, right? Where you have one person delivering content. There's some unicast stuff happening too if you have chats or you can do voice feedback or whatever, right? But it is moving out. Implementation, it can still be done unicast, right? But that is a good example. What's the other types that we could have?
Broadcast.
We can have broadcast. What's the difference between broadcast and multicast?
Broadcast everyone. multicast
Broadcast
selected
goes
ones.
to everyone.
Whether they want it or not.
Whether they
Multicast,
want it or
you're generally
not.
hitting a port and everybody's looking for it, right?
Correct. And then the other weird one is Anycast, which is, huh? Anycast. Anycast is really specific. And in those, as we go to broadcast and multicast and Anycast, right, that what we're talking about at that point is probably isolated parts of the internet, not the entire internet itself. Because you have to have an implementation in this. The router has to know if I get a broadcast packet, I need to send it to every port. And it has to not only know, but it has to also comply, right? So it's not just building a service at one end and having, if you got an app to everybody in the world that accepted a broadcast app, it still isn't viable because you need the routers to comply in the middle. So, what's the #1 goal in any algorithm in the network.
Effective
General-
use.
Huh?
Effective use of what you're doing.
Oh, it's a secondary goal. Secondary goal is effect, number one goal.
Connectivity, reliable.
Yes, reliability or correctness. Doesn't matter how efficient your algorithm is, if there is a portion of your network that, for whatever reason, doesn't work. Right? Number one goal is correctness. We could come up with a whole lot of like machine learning algorithms, right, that were fairly accurate and could deliver packets across the network really, really fast, so long as you're not on the receiving end of not being in that sample set. Right? Correctness is an absolute priority. All our algorithms have to do that.
Are we talking about packets getting from one location to the other?
Well, and yes, but bigger than that. We're talking about not just packets. So we could have some kind of application that uses like UDP, and we don't care that something designed, but that is still correct because we decided we didn't care, right? But we're talking about networking topology. How can I, on one end of the network, talk to somebody in China on a different end of the network and ensure that while I'm perfectly willing to send them a UDP packet and it get lost in the network, I can't accept that I can't reach that destination at all because something in the network is broken. So, and then comes all of our efficiency, right? And efficiency can be broken down into, are we filling our pipes, right? Bandwidth allocation. Is everybody treated somewhat fairly? Not necessarily entirely fairly, but somewhat fairly. And when I say somewhat fairly, means that if I am on one end of the network, I can send it to another end of the network and it actually arrives. There's no, somewhat fair means that it does in fact arrive. It's not real true fairness, which is it arrives as fast as everybody else's stuff. Efficient paths, right? Which really comes down to utilizing bandwidth well, again, so that we're not going across 10 million miles of wire to reach the destination. Because the longer paths that we take, the less efficient our bandwidth usage becomes. We could take a really long path sometimes if the connections are really good and still have it arrive faster. But the idea is balancing all that out. It has to scale, clearly, otherwise we could use spanning tree. It might not be totally efficient, but it's simple and it works. But it doesn't scale well. And it needs fast convergence. When I say fast convergence, what does that mean?
When changes happen, you can apply the changes as fast as possible.
Yes. So when changes happen in one area of the network, those changes are applied in other areas of the network. And it turns out that that's a not easy problem in routing. We can quickly discover and converge fairly fast on a number of pretty simple algorithms when the networks are new. So we add a new device to a network or we turn on a new network. So either new case, whether it's a new device, an existing network, or that. They don't converge well when something dies. That actually is a problem, and we'll talk about that. All right. So I am going to attempt to draw this. we have a network, right? It is somewhat, not fully interconnected, but it is somewhat interconnected. And we have multiple paths to different destinations. So if all paths were equal, then we could probably design a network where we could simply find the shortest path. So what is the shortest path to E from A? It's direct, right? Shortest path. And to C from A?
ABC.
Right? Shortest path. Pretty easy, right? Huh? There might be some ties. Right? So this could be a tie, A to E to C, right? Both are 2.
So we're talking about the shortest path in terms of hop count, right?
So it just in terms of hop count.
Okay.
We're gonna make it more complicated. So this is just in terms of hop count, right? So A though may be in Los Angeles, E is in Chicago, C is in Texas, right? The deal is it's not just hop count, it's not just distance, right? Because A may have a really slow link to E. Let's say A goes through something not super efficient, right? I don't know what we picked that is, but whatever. It's older technology, and we assign it on a scale of 1 to 10 as a 10. And we're just going to use simple numbers because we could actually calculate bandwidth, right? But then we'd have all these crazy bandwidths up there. We can use simple numbers to actually get through it on in our heads, and then the algorithms, they don't care how complicated numbers are. And let's say that between A and B is 4. Between B and C is 2. And then we have a 2, a 1, 2, 2. They're the financial networks, so they get this New York and Chicago right there. 3, 3. Oh, there's no. So now we have a much more complicated network.
Well, we have BE is missing.
Oh, B, E, and U, that is definitely missing. That is 4. So now, what is the shortest path to E?
ABC, E.
A, B.
It's A, B, C,
C,
E, right? Because it's 7, right, which is less than 10. And what is the actual method right now that we're going to use? We simply add all the numbers up, right? All the paths that can get there. So it's A, B, and we're going to E, right?
Yep.
E is how much?
8
8. A,
to the E.
B, F, E?
Oh,
No, it's
no, AE, we have 10.
7. If you take the shortest part, right?
Oh yeah, we could just have AE too.
Yeah, AE. Then A, B, C, E.
Let's just,
You're right.
let's just write a couple of, it doesn't really matter, because 8 is the right number, right?
What?
We got 7
A, B,
as
C,
well.
E is
A, B, C,
4, 2, and 1 is 7.
Okay, A, B, C, E equals 7,
Yeah.
and what else?
A, B, F, E.
A, B, F, E, 9.
9.
And then on here it has A, B, C, D, E.
10.
C. Yeah, 4, 2, 7. Yeah, 9.
Right. And this is
Okay.
on a network that is at 6 multi.
So, all those numbers are 10 as cost, right?
Yeah, they're just costs. It doesn't really, in reality, the cost would be something other than 1 to 10, right? You could put it on a scale of 1 to 10, or you could just use actual bandwidth, right, and latency and all sorts of other things, right? But really what we're talking about is there needs to be some way for us to find the quickest way here. Right now in our, what, 1, 2, 3, 4, 5, our 7 network, right? We came up with 5 different solutions to arrive at one place, right? And now imagine that you propagated that to millions of nodes, right? It is simply, you can't just calculate every different cost and reach and say, oh, there's the best one.
Just do a trace packet.
Okay, so.
Huh?
Just do a trace packet, look for the shortest.
So the question is, that's actually a good answer and not a good answer, because yeah, we could do trace and just look for the shortest one, but the fact of the matter is you got a chicken before the egg, or whatever. You have to, in order to get to the endpoint, to get that trace, you have to have a routing table in place, right?
So for this, is there like a threshold in calculating the routes? Because there's another route that we're missing, but it's more than 10.
It's more than 10. And some of them would, you could shorten it down as if you loop back to a node you've already been before, don't count that. If you loop, right, because they're technically, if you're allowed loops, then you can have infinite ones, right? So, weirdly though, or not so weirdly, if you think about it, there is a property in this type of diagram called optimality. And optimality says that if you find a shortest path in the network, then all subpaths in that network are also shortest paths. So in our example from A to E, we found that A, B, C, to E is the shortest path. That means that the path from ABC is also the shortest path. The path from AB is also the shortest path. The path from BCE is also the shortest path. And the path from C to E is also the shortest path. So in doing our one horrible calculation, right, we didn't just arrive at one answer, we arrived at several answers. And the question is, how do we use that property to make this routing question easier? Because remember, there is no central authority on routing. There is no master machine sitting over the network saying, this is what routing is going to look like, right? All of these machines are deciding it independently of each other.
And that can change over time.
We'll deal with changes. Changes are actually the hardest part. Discovering is the easiest part. Changes is the hardest part. So the question is, how do we design an algorithm that discovers this property? We're not going to design it well yet. We're just going to design an algorithm, the easiest way. We want a path from A to everywhere. So how would we go about, and if we can design a path from A to, if A can discover its path to everywhere, then B, C, D, E, and F can also use the same algorithm to discover its path from everywhere. So how would A discover the best path?
You can flood the network.
Huh?
You can flood the network.
You can flood the network. You know, you can flood the network and then use like traceback to find which, hey, of all my responses, this is the shortest one. But remember, there's going to be lots and lots of responses. And we're also going to tie up our network.
You just start with your neighbors.
Well, we're going to talk to our neighbors because you're going to find that the easiest way to do it doesn't scale well. The best way to do it is to only talk to your neighbors. That also introduces other problems. So we could simply say, hey, I don't know what any of this is, right? Because I'm A and I just got put online. A is a routing device, not a network endpoint, right? And it's going to say, hey, I want to discover how far everything away from me is. So in an algorithm sense, how do we actually achieve that? Normally, when you're trying to find a minimum, how do you achieve that?
One hop.
Huh?
You can start by sending out a one hop broadcast.
We're going to send it out, yes. But in any just generic computer science, you want to find a minimum, what do you do?
Compare two numbers and take the small.
You compare two numbers as take the smaller way. Algorithmically, what number do you start out with?
0.
Huh? So x is equal to what? So x is equal to something really big, right? Because x has to be, yeah, it has to be max, right? So let's just call this whatever. It's max. X is max. Now we discover, we write a table A, B, C, D, E, F, G. So A is trivial, right? We have a special case for being ourselves, right? And so we just say that the route to that is 0 because A to A is always 0. So now we go to our nearest neighbor. What are our two nearest neighbors? B and E, they are one hop away, right? So we go to B and E, and then we say, hey, these are all x for infinity. And they say, hey, how far are you away from me? And B says, 4. Right? 4 is less than infinity. Somewhat substantially less, right? And so we mark that at 4. And then E is how far?
10.
10. So B becomes 4, C still infinity, infinity, 10, infinity, infinity. Right? This is round 1. Round 2. Have the people that you contacted ask how far away other things are from them. So what is B's neighbors?
How did the come down again?
The direct link.
It has a direct link right here. Right, A talks to A or B and E. Now B is not only a neighbor, right, but is also the closest neighbor. So instead of talking to both B and E, now we just ask B, since he is our now favorite because he is closest, how far away is everything from him? Right? So B says, well, G is 3, and F is 3, and E is 4, and C is 2. So that sets all the values to what? So B tells A that E is 4 away, but of course B is also 4 away, so it's 4 plus 4. So that becomes 8, right? So we kill that, and in round 2, this is B here. In round 2, this is 4 plus 4, so it's 8. And where's G? 7. Where's F? 7. And D?
8.
No, we haven't got to D yet, right?
Infinity.
It's still infinity. C is 6. Then, what is our lowest count now in column 2? C for 6. Now let's ask C, who is his neighbor's distance. Right? So C says, hey, D is 2 away from me, and C is 1 away from me, right? So this is round 3, and now we're at C, which is 6, right? So what do we learn? We can't get to G from C. We can get to D, E, and back to B, which doesn't count, right? So C to D is what?
8.
8. And E? 7. Right? Because C's at 6, so and C's 1 hop has a cost of 1 to get to E. And did we learn anything else from C? Nope. So now, what do?
We have 3 7s.
We have 3 7s, right? Pick a random one. Let's pick G, because it's over here on the left, right? So now we pick round 4, which is G7, and we figure out how far things are away from it. How far is F?
11.
Lots of answers. G7,
Yeah.
that's this one right here, right? So we're gonna go to F.
11.
It's 11, right? So G7 is 11,
So no.
so that's a big fat no, right? So we just keep it the same. We finally find a minimum, right? And where else can we get from G? Nowhere else, because we just go back to B. Right? So then we pick another 7, right? Which can be F. So round 5, F7. F can get to back to G, which doesn't count. So it can get to E, and that's it. Otherwise, we're back to B. So E goes what?
9.
9, right? So 9 isn't lower than 7, so we keep 7. And then we have 1 7 that's propagated out, and that is E again. So 6, we get E7. So from E we can get to F with 2, right?
Mm-hmm. So
Which is 9.
9. So
We can get to D with 2, right?
we can get C
which is
with
9.
8. Well, no.
And we can get back to C and back to B. Those don't count. Remember, we're keeping all. When we keep these, there's actually an implicit route in here. So B was 4, and then C6 was actually BC6, right? And then we're keeping all of those. So you can't go back to a node that's in your number, your top number already, right? And now we've reached a point where we've covered the entire network. And each of these, by the way, in your text is referred to as relaxing. So finding the minimum is relaxing. I guess because it's easier. Right, but it's really just find a minimum. And when you want to find a minimum, you start with a very large number, and then you start drilling back down.
So is it always n minus 1 for the total number? It took us 6 times for 7 nodes.
Correct.
Okay.
So what happens if we have to do millions, right?
Yeah, that's
That would suck. So the problem is that method doesn't actually work. Does anybody know what that method's actually called? Well, it does work, but it doesn't actually work with very large networks.
Distance vector routing.
Oh, we're about to do distance vector routing. Oh, right before that, it's the guy's name. Dijkstra.
Thalman?
So next we're going to do distance vector routing.
Traveling salesman dude.
It's the traveling salesman dude, which eventually was vindicated with his NPR problem. So, what if we just did it via neighbors? So in that particular one, we had to ask every single node on the network a number of questions, which is n minus 1. So every single node on the network, we'd have, if there's a million nodes, we have to ask them a million minus 1 times. And that just solves A's problem. That doesn't solve B's problem, right? So from B's, we could extrapolate some answers that if A has the shortest path that involves B, then B also has some, because of the property of, what do I call it, optimality. So optimality, so because of that property, we can extrapolate, because B is on the shortest path from A, then all of A's paths that route through B are also shortest paths. So we could do that. But what happens if poor G is not on A's shortest path? And how do we actually get that message out to everybody? So the idea here is to listen to your neighbors and what they think shortest paths are. So let's do a smaller network this time. So now A, which is right here. I got it. B, C, and D. Let's start out again with a table. And we have an if statement for our A. I am the shortest route to myself. And then we set all the others to infinity. we ask our neighbor, or our neighbors in this case, how far are they away? And remember that our neighbors are going to be also running this algorithm, and they'll ask how far their neighbors are away. So we, on our round one, we get B says I am 3 away, right? And D says I am 7 away. He doesn't learn anything else about the network. In the same time, B and D are asking these same types of questions. So B asks A and C, how far am I away? And so you got a different table for B. And also D, because we have a direct connection from him. And C asks the same question, and D asks the same question. And they're all asking the same questions. So from those other questions, instead of asking only on A's behalf, we're going to ask, we are going to pass information to our neighbors.
So, in the case whereby A asks B, when it's B's turn to create the table, B does not necessarily have to ask A because the information is already shared.
The information is already shared, yes. So A asks B, and then B also passes the information when it learns of how things are close to them. So B has the information on D and C, as well as A, but it's not going to pass the trivial information back to A. So B says, hey, I have a route to D that's 3, and also a route to C that's 6. Right? So then we get, much like in the last case, we get a message block passed, and C becomes 9, right? And D becomes 6, right? Because it's 3 plus 3.
Is this all part of round 1, or is this now round 2?
This is round 2.
How did C become 9 again?
3 and 6,
Oh.
right? It eventually will be better. Right, but all these packets are getting passed, but they only get passed to neighbors, right? And so B or A learns about packets that B can pass, but B will eventually learn, if the network was bigger, what D, E, F, and G can also pass, because they are passing information to their neighbors. And so now A is sharing information not only itself, but what it's also learned from its neighbors. If anything was on the back side of over here, then it would pass that information along. So if you do that, it looks a whole lot like building our last network, right? We simply just add, we pass networks, and we don't always have to ask on A's behalf, we just share our adjacent information. And we can build a network that way. The problem is that what happens if you're doing it this way when one node dies?
It goes down the direction, the closest, shortest path.
Well, that's what we would desire to happen. What actually happens? So remember, what if A dies? A dies, B is still passing information about A, and so is D, because they're neighbors. A dies, right? And there is no, it's offline. There is no valid path to it. But B and D both believed, because A originally told them that I have a good path, that there is a way to get here. So what happens in this type of interaction is you reach convergence when all the let's say we reach convergence and we get a fastest route and we have a built out table for all the nodes. And then A dies. right? So then they're like, hey, something's wrong, and we need to start passing packets back and forth again to see where is where. The problem is B and D both think A is still alive, and so because there's A is still alive, we can keep routing between B and D and C, trying to find new routes to get there. And so we just increment hops and increment hops and increment hops. And you end up with a counting to infinity problem. And so while the method of that we're explaining here for distance vector, while that method is great to discover a network, it does not work well to have convergence on a network that's being disabled. Adding new things, totally fine. Things dying, not so good. So, what do you think was the solution for this?
Reduce the number of the infinity.
Yeah. We pick an arbitrary number on our network. And the number, by the way, because this was actually implemented in RIP, the number was just picked as 16. And why was 16?
Maximum hop and breadth is 15, so you just add 1.
Correct.
Yeah.
So it was maximum hop count was 15, so we just add 1. Say if we get to 16, then it's dead. But it doesn't converge well because, and it also doesn't scale well. But it's actually was implemented in RIP, which is super easy. If you guys want to go out and look at the RFC, it's super simple. What do you think is a better solution? What piece of information do we have that is a better solution? The problem with broadcast though is you can either implement it in all the routers or and basically flood the network, and we'll talk about flooding. But we have one key piece of information from a lower layer that we haven't used yet. Huh?
Yes.
Which layer? The link layer. We have one key piece of information that we haven't used yet, and that is, are you online? The link layer can tell you you're online. When you plug a cable into into a new switch, right? The switch comes alive, right? No IP information has been shared. The switch comes alive. We have a piece of information that we have yet to use to fix that problem.
Doesn't this break down the whole separation of layers idea though?
We are gonna build it up and then tear it down.
But
Wait till we get to security.
how many times is it gonna ask the switch?
Huh?
Are you live? That's gonna be so much traffic. If we have like a
You only ask your neighbors if you're live, and that's at the link layer, not the IP layer. That just happens. It already happens. We already discussed it. What happens when you connect a switch or a new device to the link layer, right? At the data link layer, that information is already shared. So if it goes down, then you can simply at the link layer say, hey, are you still there? And if you look at internet traffic, or not internet traffic, if you look at network traffic with Wireshark, you'll see those packets being passed. There's a timeout, and it just says, are you there? And it's really fast, and it doesn't take too much. But we'll use that, and we'll start building a modern network now, modern routing network. No, pinging is still ICMP. That's routed. No, at the link layer. The link layer exchanges information, right? We talked about this is how we found things at the link layer, and we talked about the problems which we introduced spanning tree to fix, right? But these are link layer issues. So things that can talk to each other at the link layer are by definition on the same network. They don't need the IP layer to work. A router sits on 2 or more existing networks, depending on which port it is, and divides those things out by different MAC addresses. But at the link layer, they still function just as if they were on the local network. Even if it's some weird point-to-point optical protocol,
Yeah.
sonnet, whatever, they still exist at the link layer.
We assume that A is down, but what if A is advertising like wrong information or wrong routing information?
We'll get to all that stuff with security.
Alright. So will the MAC layer solve that?
Huh?
Will the MAC layer will solve this problem too?
So it will at least solve that A is having,
A is down.
in the problem that A is no longer routing.
Okay.
It will solve that problem.
Alright. Good.
The question is, how do you stick things on there how do you ensure that A is playing nicely would be dealt with later. And this is when we're gonna break all the nice, pretty layered cake that we made.
So even at the link layer, we have discovery, right?
Mm-hmm.
And that discovery is being sent out every now and then to check.
Mm-hmm.
But that will only work if we're dealing with, say, like an internet network, which is like a line. If we're dealing with like the whole internet, then that's going to be.
But each link, remember that, yeah, each box in my thing you're really tired of so far, right? This is a link layer, right? This is a link layer. That doesn't mean these connections are operating at the link layer. It doesn't mean that this one is the same as that one, right? Because they could come in and have 2 total different link layer technologies, right? But it does mean that this and this one is the same, and the same with this and this one. If it wasn't the same, it had to go through another device, and then we would just add another box on there. You can't take one physical topology and transfer it to another physical topology without a device there, and that device has to exist on both.
Yes, I'm having a problem with my coding right now. That was why I asked. Sorry, it's not part of the class.
All right. So we decide on 4 questions or 8 questions?
4.
Alright,
Okay.
Let's debate now.
Hold on. Everybody for 4. Don't raise your hands twice.
Ah, you just do it twice. It's like
8, 9. Okay. Everybody for 8. Oh, you guys lost terribly. So I'll send out the questions tonight.